So I was tasked to present an overview of the capabilities of one of the biogeochemical models that is used by CMEMS, which is the PISCES model. So Coralie Perruche presented already an introduction to the model this morning. So PISCES is a model of intermediate complexity which has been designed for carbon cycle studies and ecosystem studies. So the model is used by an international group of users for a variety of applications that span from short-term forecasting over climate projections all the way to paleoceanographic studies and timescales. So I will exemplify the scale of the model, which is of course quite a task, by showing output from several model applications. And I will also, whenever possible, I will always give references to publications. So everything is published and is accessible, and I invite you to follow up on this for more information. So CMEMS is a monitoring program, as we know, and one objective is to monitor the present-day ocean variability from one year to the other. That's where the ocean state report comes in, and also looking at reanalysis to assess the variability at the interannual level over the past 10-15 years. So there the time span is bracketed by the available observations, for instance satellite records. So we want to pick up anthropogenic trend. And I put this slide up to remind you that, of course, the anthropogenic climate change is like a continuous trend superimposed of the natural variability of the marine system. And this natural variability itself occurs on very different time scales. You have short time scales, days of weeks, then variability seasons to decades, so seasonal cycle, of course, interannual variability of natural climate modes like NAO, PDO, etc. And we go up the horizon to centennial projections. That's the IPCC time frame up to 2100 and beyond. Each of these time scales has specific expectations from society and applications tied to this. So if you want to know something about harmful algae proliferation, jellyfish, ocean acidification events which might impact your particular setting if you have an agricultural site, for instance, coastal hypoxia, larval drift. So this is the time scale of days to weeks. Synoptic variability, seasons to decade is more targeting issues like changes in marine productivity, biomasses, fish stocks, the turnover from the industrial side of industrial like processing plants, fish processing plants, fishing gear, fishing fleets. All these investments are on decadal timescales. So personally I find that's a really relevant timescale here, the decadal timescales. Centennial projection, it's more like what-if scenarios at the horizon of 2100, which is also important to know for society to have the broader perspective into which to cast our adaptation measures. So that doesn't work. So along with this comes from the model world, it's a different model it's quite different from the model perspective. If you have a model system, I don't know if you're all modelers in these rooms, so you all know that the model is a numerical simplified representation of reality. Sorry, you will get the PDF, so there's no need to make pictures of the screen. You can do, but it's really not necessary. Oh, if she's sweating, then you can do. Of course, sorry for that. So, what I'm saying, the model is a numerical simplified representation of reality, and the model has its own solution, which is not reality. So if you want for an application to be very close to the observed state, we stay close to the initialization of the model. The model is initialized like for the Siemens product with observations. We are close to the initial state, it's an initial value problem. We have the forecast here up to several weeks. As the model is run out in time, it's going towards its own solution, it's going away from the observations. The ultimate end member here is the long time scales, like 2100 and longer, where the model solution is very much controlled by the model internal dynamics. So here we have a fully coupled Earth system model. I will show some examples later on, which has its own climate. In between, we have this space here of decadal predictions, which is something that is emergent, it's picking up speed in the community since the last IPCC report, where there has been the chapter on decadal predictions on the physics only, but the climate institutes like the one I'm coming from, IPSL, but also the German colleagues or the colleagues from US are also looking at biogeochemistry in these systems. So what it's done in the community is to have a coherent model suite to address all these timescales. In our case, it's the NEMO system, OPA for the ocean, LIM for the sea ice, and PISCES for biogeochemistry. So Siemens is focusing on this time here. So it's an initial value problem. So we have seen examples of this morning presented by Coralie Parrish. So I think she made a very nice presentation, and I won't repeat her content. And we also have seen application on this and discussions. So I will directly move to the model skill. What is the capability of this component PISCES to reproduce biogeochemistry? Knowing that PISCES represents the first levels of the food web, phytoplankton, and then zooplankton as grazers. I remind you, two size classes of phytoplankton, the silicifiers diatoms, the non-silicifiers nanophytoplankton, which can also fix nitrogen, atmospheric nitrogen, the isotrophs, and which also produce calcareous shells, so calcifiers. And then coupled to this, two zooplankton size classes, small and meso-zooplankton. So if model skill, as I said, it's a big endeavor. And I was thinking about how to structure this, and I propose to exemplify certain essential ocean variables, because there's also a link to Siemens and to the Global Ocean Observing System, these initiatives. There are several variables. I think 8 or 9 for biogeochemistry. I won't discuss them all. There's one group, it's called the inorganic macronutrients. We have nitrate, phosphate, silicic acid, ammonium, and nitrogen dioxide. So all these, at least the 3, 4 here, are modeled by PISCES. Then we have here a set of supporting variables, which are also model output. But I invite you to look at the societal drivers of this. The motivation is we want to know as a community what's the role of ocean biogeochemistry in climate. So climate feedbacks through the exchange of climate active gases like CO2, but also N2O at the sea-air interface. We want to appreciate the impact, human impact on the ocean biogeochemistry, so modification of these exchange fluxes on longer timescales, but also issues like eutrophication, which also then relates to the ocean ecosystem health. The applications, how is the ocean carbon content changing? What about the expansion of low oxygen zones like dead zones? What about ocean acidification events, changing in ocean biomass, the coupling to higher trophic levels, eutrophication and pollution? So I present here nitrogen maps, so results. This here is the observation, it's the climatology from the World Ocean Atlas, and here you have results from PISCES. So this is the presentation of the PISCES version 2, so the latest version that has been published. And this is a climatological simulation. So this is far away from Siemens products. As this is the simulation has been realized with a climatological physical forcing field, which is like a typical ocean circulation which has seasonal variability, but it's no interannual variability. Okay? So this has been, the model has been run for 4,000 years with this normal year, so to speak. No interannual variability. And I drew this up because what it shows is somehow the numerical solution of this model biogeochemical model PISCES. And this capacity to produce a solution, a model solution, a model state which represents the observations. So this hasn't been initialized with observed distribution. It has been, the model run has been initialized with constant distributions of nutrient traces in the ocean. So the structures are really reproduced by the interaction between biogeochemical processes and ocean circulation. So the model reproduces the observation to the extent possible, within the limitations of the biogeochemistry and the ocean circulation. Just to tell you something about time scales, if you use a tracer like natural C14, which is produced by radioactive decay in the atmosphere, to look at the time it needs to equilibrate the deep ocean in a model, you have to double this 4,000 times, 2. You're going into 10,000 years of simulations to get something that is a solution, a steady state solution of the model. So all this to say that here we have surface ocean nitrate observed in a model. You see it's a reasonable, correct representation. This here is a section across the Atlantic. It's an average concentration field, and here also in the Pacific. And what you see here, you see the oligotrophic dryas, of course, popping up. You see the formation of deep water around the Southern Ocean, which is a high nutrient, low chlorophyll area. So we have high nutrients propagating to the deep. And we also see, of course, some model differences. So I invite you to check out the paper for more details on this. The next EOV I would like to mention is dissolved oxygen, because there, of course, you all have aware of coastal hypoxia, which induce large fish kills. So this is really something of societal relevance. And now if you look at the oxygen produced by the model in the climatological setup, see that the ocean, the surface oxygen distribution here is rather well reproduced. So I would like to highlight something that whenever you see a surface oxygen field, the surface ocean is mostly controlled by thermodynamics. So if you get the temperature right, the SST right, and the salinity, but mostly the SST, then you get a correct representation of oxygen solubility. Then, of course, you get a correct representation or satisfying representation of oxygen content in the mixed layer. It's different if you go to the ocean interior, where oxygen again reflects, as the nutrients too, the interaction between biogeochemistry and ocean circulation. So biogeochemistry, some traces like oxygen, is like a magnifying glass that you put on your physics because it amplifies biases that you have in your physics. If you look at this here, overall, it is not bad. But what you see, like here, just look at this panel here, the Pacific, here the observations, here the model. You see that the model overestimates the oxygen content. This is due to a too vigorous ventilation around Antarctica. So the model feeds in water masses which are too rich in oxygen, which then spread across the basin and are responsible for this positive bias in oxygen concentration. Now you can go further in this analysis. Why is there too much deep water formation? there is another analysis, another paper that you will come up later in my presentation, which makes the link with the bias in this model in salinity and temperature, so in density. If there is an excess density anomaly, positive density anomaly, you will form likely too much deep water, entrain too much oxygen, etc. So all these processes are obviously linked, as we know. Another EOV of great interest, societal impact, is the carbonate system. So the carbonate system is dissolved inorganic carbon, total alkalinity, departure pressure of CO2 and pH. And of course, there we have RC fluxes of greenhouse gas CO2 and ocean acidification, just to mention the two most important. And I would like to exemplify the skill of NEMO PISCES to reproduce the carbon cycle by a different type of simulation now. This is here a coupled physics biogeochemistry simulation, so NEMO PISCES coupled. What I show here is at half-degree resolution, global. This simulation has interannual variability. It is forced with a forcing product based on era interim from 85 to 2002, and after 2002 is extended to 2012. If you want to study the carbon cycle, we need to get the anthropogenic component of CO2 correct in the model, right? So we know that since the outstart of industrialization, we are using fossil fuels, cement production, etc., result in a release, continuous and increasing in speed, release of CO2 to the atmosphere, so the atmospheric content of CO2 increases. So we need to get this anthropogenic carbon transferred from the atmosphere into the ocean. So in order to do this, we adopted this model strategy here. We have one spin-up loop with constant pre-industrial atmospheric CO2 over one reanalysis cycle. And then we start in 1870, and we loop the times needed up to 2100. We loop over this forcing cycle. And this allows the ocean to build up its own anthropogenic carbon. This here now is a comparison between a model output, so this half-degree model here. There we have a meridional transect shown on this panel. This is the two bias maps. This here is database products by Landschützer et al. It's a recent one. It's based on a neuronal network. And this here is the Takahashi database as shown earlier this morning. So, of course, we get the main uptake regions for CO2. So this is total CO2, the natural component anti-anthropogenic. We have high uptake in the high latitude. We have high uptake fluxes in the high latitudes, as shown here, in the observations, and in the model. We have outgassing in the equatorial band, very pronounced in areas of upwelling. The model reproduces that also. And if you look, it doesn't really show up very well here on the screen. There's also some outgassing in the Southern Ocean, specifically here in the Takahashi product, a little bit less in the Landschützer et al. And that's something that the model fails to reproduce. So once we have this, our simulation strategy, which combines, forgot that to say that, one simulation with constant PCO2 all the way to 2012, and one which has this increase of anthropogenic CO2 added to it. So the difference between both, total minus pure industrial, yields anthropogenic. So this approach allows us to access directly, as shown here, for the global ocean is a panel for the coastal ocean. This is the global ocean. The exchange fluxes of CO2, the total here in black, and the anthropogenic in red, and the natural here in blue. So what you see and what we expect, the ocean takes up CO2, the excess CO2 everywhere, but there are regions of pronounced uptake and pronounced spreading of this anthropogenic signal to the ocean interior, one being in the Southern Ocean here, and the other one being in the North Atlantic, linked to the Modewater Formation and the northward transport of these then CO2-rich waters and the downward delivery at sites of deepwater formation. So if we feel somehow confident on the model capability to reproduce the observed state, we can go towards projections, and I'm far behind time, so you have to speed up. So I show some example here from this other end here of the time scale, which is centennial projections, so IPCC time scales. And this is model results obtained with the coupled Earth system model. So as I said, fully coupled, it creates its own internal dynamics, its own climate dynamics. These panels here are busy. You have the different IPCC scenario. Just focus on the red one called RCP 8.5. That's what's called the business as usual scenario. So we keep on emitting CO2 and other greenhouse gases as the level as we do now. And behind these scenarios, you have, of course, pathways of economic development as well. So we look at this red one. Global sea surface warming, pH, primary production, oxygen content. This is a multi-model analysis. So in the realm of climate projections, what the community does now, they use multi-model ensembles in order to get an idea about the robustness of the projections and also the uncertainty associated with those projections. So we have the multi-ensemble says a sea surface temperature increase of 2.73 with the multi-model standard deviation added to it. See, this is the red bar, quite some uncertainty. The oxygen content globally goes down by roughly 3.5%, which is not much at the global ocean, largely in response to warming and decrease in solubility. But what's this small number hides is the potential extension of oxygen minimum zones. So this is a little bit misleading, because if you want to have an idea on what's going on really in terms of impact on the ecosystem, we have to look at a much finer scale and also at the regional scale. The pH is going down by minus 3.33, sorry. And the integrated primary production 8.6, you see here, there is a large uncertainty when it comes to projection of primary production. This is how the surface maps look like. The stippled areas are areas where all models agree. What you see is directly that they agree in pH everywhere. That's normal, between quotes, for the surface ocean, because the pH changes in response to CO2, and that's largely driven at the air-sea interface by the atmospheric content of CO2. If we just jump to the primary production here, there are also large areas of agreement. And the common pattern that's out of projections from this is the past IPCC report, I forgot to say, from this one and also from older projection already, is this seesaw picture where you have large decreases in NPP at the mid-latitudes and decreases in the mid-latitude and increases at the high latitudes. And that's decreases over here are linked to an increase in stratification, a decrease in nutrient ejection into the euphotic layer, and then a decrease, of course, in production. In the high latitudes, it's the opposite. And that's because in the high latitudes, the increase in stratification has the tendency in some models to alleviate light limitation. So it favors production, and also the growing season is longer because of the retreat of sea ice, the loss of sea ice. So we have talked about projections and what we want to know, and what our one objective of the monitoring exercise is to pick up trends, to identify trends in time series in response to climate change. So the question is, how long does a time series need to be in time series of observation or a reanalysis. And this brings me to another study done with PISCES, which I think is also interesting in terms of evaluation of the model, because it shows a more subtle way to look at things. This here shows the anomaly of primary reproduction as seen in the COST-EOS satellite record over the stratified ocean in black and the global ocean in green. And here on this panel you have the anomaly in SST and stratification index. See that here the axis, the sign of the axis is inverted, because of course if you have a strong positive anomaly of SST, for instance due to El Nino event, we have a strong decrease in productivity. So this is the satellite record. This now here is the Earth system model. As you can see, the phasing is not perfect. I'm behind, sorry. The phasing is not perfect because the model has its own internal dynamic. However, the relationship between stratification and production anomalies is reproduced by the model. As seen here, on this panel here, COST in black and red the model. You see that the fundamental underlying relationship is picked up by the model. So now, what do we want? How long does a time series need to be in order to pick up a trend from climate change? Draw up this study by Hansen et al. So I invite you to look it up. Here this panel shows tendencies change derived from satellite record for chlorophyll and NPP. And on this panel you see the year when the change introduced by climate change in NPP or chlorophyll exceeds the envelope of variability in the model. In order to do this, you need a long simulation with Earth system model, long enough to get a statistically robust idea of the variability, the supposed natural variability in the model, and you need a climate run simulation, and then you can deconvolute both signals. Red means areas where it doesn't get statistically significant. So the take-home message here is you have different models, you get different results, because the variability in the models is different from one model to the other. And this is low resolution model. So if you increase in the resolution, the variability is larger, and the horizon where you can actually detect the climate change signal is getting further in the future. So the take-home message is that there is very little prospect to be able to detect statistically significant, in a statistically significant way, a signal of climate change in a satellite record any time in the coming years. We need to extend the time series. And the same holds for reanalysis. And detection is one thing, then to attribute this statistically to climate change is yet a different issue. So it's not something that we will just detect next year down the road. Quickly, the other area on this time span here, the Decatur Predictions. This is a study that has been done also with the NEMO-PISCES Earth system model, also the configuration used for the past IPCC exercise. But it contributed to the Decatur Prediction exercise. So the Decatur Prediction exercise uses ways to initialize the model. So to call it, to tie it back to the observed state. Initialization is the guiding of the model along the trajectory of observed natural variability. And in our group, this has been done by nudging observed SST or correcting modeled SST with respect to observed SST, but only in the equatorial band. And this is the result. This is the temperature, surface temperature in the El Nino tree box in the equatorial Pacific. The stippled line is the free Earth system simulation. And you see we are a little bit, to say the least, off from the observed state. So the nudging of only SST in the equatorial band phases the observation, the model, which is now here, the thick black line, to the observations, which is shown in brownish, in the brownish color. So it's a broad line here because Roland Séphérion used various different observational products in order to bracket the uncertainty linked to temperature reconstructions. So here we initialize only temperature in only the equatorial Pacific, and this has a benefit on biogeochemistry globally. In the global ocean, as shown on this slide here, which shows NPP of the time span of the satellite record. Again, stippled is the free simulation. Green is the result of various satellite capture satellites. And the thick black line is the nudge simulation. So, I mean, you see that this initialization of physics has a direct positive impact of biogeochemistry. So what is done? We have a continuously nudge simulation if where the SST is corrected, and every year at a specific start date we stop the correction of the physics, we stop the nudging. And then we have an ensemble of free simulations starting from that day, and this ensemble is obtained by slightly perturbating or the SSE correction. And the simulation is run free in time, and you compare with respect to the nudge simulation, and you look how long is the model, the free simulation, capable of following the nudge simulation in the future. Then this is just an example here. It's a correlation between the free and the nudge simulation at year 1 for NPP and for SST. For SST, you have a high correlation in this equatorial band. That's the capability of the model a year in advance to somehow predict the SST in that box is the retrospective forecast. And this is the corresponding picture for NPP. Also see some scale here in the Pacific. And the stippled lines here, the gray shading that you barely see, areas of major tuna catches. The same done at 2 to 5 years. Quickly have a look at SST. You lose the predictive capacity of the model, but you maintain it for NPP, which in the paper, with many more arguments, allows us to conclude that SST can be predicted up to a year, which is coherent with the timescale of ENSO prediction, which is at best a year. NPP can be predicted in that model setup up to 5 years, depending on the years. Why? Why could this be the case? Well, so we nudge SST, then we stop the nudging, we have the free simulation, but the correction of SST has the impact on surface winds, which has an impact of the upwelling. So the upwelling modifies the nutrient supply into the surface ocean, and the biogeochemical system has inherent different time scales. So it's kind of shielded from the high frequency noise in the atmosphere. So we are entering into a different set of time scales. We have a slow dynamic adjustment of biogeochemistry. And there is, of course, also a direct impact of SST on growth rates in the model. So this decoupling of the fast dynamic adjustment of SST to the atmospheric fluctuation and then the slow dynamic adjustment of biogeochemistry yields a longer predictability horizon for biogeochemistry. I think this is a very interesting result also for the CMEMS community, because if that reasoning holds, and if you have a system which is largely controlled by bottom-up processes, we can go on further with this thought and saying, okay, now we couple this to mid and higher trophic levels, and as we know, the timescales involved, if you move bottom-up across the food chain, increasingly longer. So I'm not sure, I think nobody knows today whether this is a robust value, whether actually this hypothesis can be verified as being true, that the predictability horizon might increase as we go to fisheries resources. That's me, 4 minutes over time, and it's the end of my talk. The only thing to say at this point is all this has been global application, but we know, of course, that many applications and questions are regional in scope, and that will be the topic. So the link between this global to regional models will be addressed by Emlyn in the next talk.
Thank you, Marion.